In this video, I'm going to be introducing Riemann sums, specifically right and left endpoint Riemann sums. So this is an introduction to finding integrals. We're not going to get into integrals in this video. An integral is going to represent the area under a curve. And before we get to that, we're just going to use some approximation methods, and they're called Riemann sums. We're going to be able to approximate the area under a curve by using some shapes like a rectangle. So if I can find the area of one of these rectangles and I add up all of these areas, that would be an approximate area for the area under this curve. And we can see that if we were to make a lot more rectangles or increase the number of rectangles, our approximation is closer and closer to the actual area. And so the integral is going to be an infinite amount of rectangles, and so it'll be an exact amount of area. But before we get there, we're just going to approximate. So in this video, we're just using rectangles, and we're going to talk about two ways that we can use rectangles. We can use rectangles where we talk about the height of the rectangle being the value on the left side of the rectangle. It's called the left endpoint. Or we could flip that, and we could use the height of the rectangle being the function value evaluated at the right side of the rectangle, or it's called the right endpoint. So two different ways we can do it, and they're both going to give us different approximations, but similar approximations. And so let's practice doing both of those. First thing we want to do is figure out how to find the area of a rectangle when we have these curves or these functions that are curving. And so the area of a rectangle is height times width. And if we're using a left endpoint, we're actually going to use some intervals down here. And we're going to use the left endpoint on that interval. If I was to plug that value in, I get the output of my function. So the output of the function is going to be representing the height of the rectangle. The width of the rectangle is going to be represented by our change of x. So if I split up this interval into 4 equal rectangles, then I know what's called these little sub-intervals, and they're going to represent the width of each rectangle. So we're going to practice evaluating both of these so that we can find the area of the rectangle. Change of x, this width from here to here, is going to get broken up into the number of rectangles. So I can break it up into any number of rectangles, and the more rectangles I use, the better the approximation. So we'll be able to figure out what this change of x is, what the sub-interval or the width of one rectangle is, by using this formula. If I take this interval from a to b, and I just divide it by the number of rectangles, so I'm going to do b minus a divided by n, which is the number of rectangles, that's going to tell me how wide each rectangle is, or the length of the sub-interval. In a previous video, I described sigma notation. And so there are Riemann sum formulas using sigma notation. If you understood how to find the height of the rectangle using the function value and the width of the rectangle using this formula, then you don't need to understand the Riemann sum formation using sigma notation, because it's saying the same thing. But I'll explain it just in case it makes a little bit more sense. If I number my rectangles 1, 2, 3, and 4, then their x values down here, this interval, I can notate by using x sub 0, if you can read that, x sub 1, x sub 2, x sub 3, x sub 4. And so all this is saying is if I represents what rectangle I'm talking about, so for example, the first rectangle, I plug in 1 into the I, and then I have x sub 1 minus 1, which is x sub 0. So I know that I'm plugging in the left endpoint into my function to evaluate it, which is going to give me the function's value on the left side here, since I'm using the left endpoint. And then we multiply that by our change in x, or the width of the rectangle, and so we have height times width. And so that's basically what it's saying. And then we're going to sum up all the areas, so that's why we use sigma. The right endpoint formula is similar, except we're going to use the right endpoint. So if I know what rectangle I'm referring to, so for I, I'm substituting which rectangle I'm talking about. So if I'm talking about the first rectangle, I substitute 1 in there. So I'm evaluating x sub 1. And as you can see, that's the right side of the first rectangle. And so that helps us evaluate the function at the right side of the rectangle and gives us the right endpoint. So that's our height, and then multiply by the width, the change of x, and we get our rectangle area. And we sum up all of the areas of the rectangles, and we get our approximation. So let's do some examples here. So here's some steps you might want to follow. We need that change of x. We want that width of the rectangle. Unless the change of x is 1, this is more important. If the change of x is 1, it makes it a lot easier to evaluate, but we always want to check and just make sure. That's going to allow us to set up our subintervals so that we can plug in left endpoints or right endpoints, and then we'll find the area of each rectangle, depending on how many rectangles we're using, and add them all together. So let's use 4 rectangles to approximate the area of this function, or the area under this function, in between these two numbers, -3 and 5, or on the closed interval, -3 to 5. So what we can do is visualize it. I can draw this function on a coordinate plane. It's a decreasing linear function with a slope of -1/2 and a y-intercept of 6. We can sketch out that function, and I can visualize what area I need to find for this interval in between -3 and 5. We know we're breaking up that interval into 4 rectangles, so let's find our change of x. My interval is -3 to 5, so I'm going to do 5 minus -3 and divide it by the number of rectangles. We're told we want to use 4, so n is 4. So our change of x, or the width of each rectangle, is 2. So I know that each rectangle is going to have a length of 2 units, and there's going to be 4 of them, so we can sketch in those rectangles to visualize it. We can set up our subintervals. We know this first rectangle is going to be the width from -3 to -1. The second one is from -1 to +1. Third one is from 1 to 3, and the fourth one is from 3 to 5. So now that we have our subintervals, we're going to be evaluating our function at the left endpoint on each interval. So if I plug in -3 into my function, I can evaluate and find the function value at -3. And that'll be the height of our first rectangle, the left height of our first rectangle. And then we're going to multiply that by our change of x, and that'll be the area of this rectangle. Notice how if I'm using the left endpoint, I have an overlap here. So each of my rectangles is slightly over the graph. We'll take that into consideration when we look at our final area. So I'm plugging in the left endpoint of each of my intervals into my function, and then multiplying that by 2, and that gives me the area of each rectangle. So when I do that, I get 15 halves times 2, plus 13 halves times 2, plus 11 halves times 2, plus 9 halves times 2. And if we're multiplying by 2 and dividing by 2, those all cancel each other out. We're just adding 15 plus 13 plus 11 plus 9 and getting a total approximate area of 48. And again, because we were using a left endpoint rectangle and we have a decreasing function, this ends up being an over approximation. So we took the area of the rectangle, so all of these shaded areas is how much we are over in our approximating area. Let's do a similar thing, but this time use the right endpoint for each of our subintervals. So we didn't change our subinterval length. It's still from -3 to 5. We're still using 4 rectangles. So our change of x didn't change. It's still 2, or the width of the rectangles is still 2. But this time we're going to be evaluating our function with the right endpoint on each interval. So if I plug in -1 into my function and evaluate it, and then multiply by 2, that's the area of this rectangle. If I plug in 1, the right endpoint on my second interval, into my function, evaluate it, and multiply by 2, I get the area of the second rectangle, and so on and so forth. So we do all 4. So we end up getting 13 halves times 2, plus 11 halves times 2, plus 9 halves times 2, plus 7 halves times 2. And again, multiplying and dividing by 2 cancels, and we're just left with the sum 13 plus 11 plus 9 plus 7. And that gives us 40. So a different approximation. This ends up being an under approximation because we're using the right endpoint rectangles on a decreasing function, and as we can see, the area of our rectangles is going to be slightly under the actual area under the graph, so we call that an under approximation.